Thanks for the invitation. So I'm glad to go after the three who really outlined what a good GWAS looks like. So I don't, my point is not to talk about good versus bad in general. It's to give you first background. I'm a consumer of these studies. I'm not a producer of one. And I really like the education and the other ones that the group has done is great. My main interest is really thinking about what else to do with them. And in particular, part of the context here, as I was thinking about my presentation, is that there's a study called the Wisconsin Longitudinal Study that's recently in the works of getting genome-wide assessments itself. It'll probably be a year away, but it's probably not unique in the fact that it's a small study itself. It'll probably be 7,000 or 10,000 people, and it'll likely be a part of this consortium soon, maybe in a year or something. But asking is if that's all. If you just take these little studies of 7,000, get genome-wide information, and then send them into the consortium, and then that's the end of the story. That is an end. So like people at Wisconsin, I think, are thinking about what else would we want to do than just spend all that money to get the one bunch of million or however many they're actually going to get SNPs, and then send it away, and it'll just be one of your 60 studies that you'll take into the rest of the decade of results. So I thought I'd just outline maybe some discussion points. This might not be where the discussion goes, but I think there's probably more people like me here who might be asking themselves what they're going to do besides the good work that's already been shown. So on one hand, whether we should believe them in some larger sense, whether, if you give me 3 SNPs from education, if that tells me something about a causal SNP. I think they did a good job thinking through that. I'm going to just raise a couple of questions. And then the other two are about whether the production of GWAS results outside of the consortium, and then the use, and that's the use is related more to the polygenic scores. And again, this may or may not guide discussion about whether we think of these results as a first step or the end of the story. So I'm just using different language. I don't think this is anything different than what you've seen. So what you do is you fish, and you run a lot of tests, and you amass large data sets. And I think the first 3 presentations outlined precisely why this is exactly how you would want to do this enterprise. Some limitations that were also discussed, you focus on main effects. So in general, not too much gene and gene interactions, not much gene environment interactions in this discovery phase. And causality, if there is something called causality here, I think the standards are leveraging 3 features. One is that these variants are assigned at conception, so that whatever the phenotype isn't feeding back on the SNPs in the data. So there's a temporal part that the SNPs have to happen before the phenotype happens. So that's typical. We use that all the time in social science. There's controls, so you saw all the principal components. And then replication. So as thinking about what becomes a finding, I think it leverages these 3 and probably other buckets. And I guess my main point in thinking about this slide is just how different that is versus how we're trained, most of the people in the room. And if in the sense of what we believe and what we don't believe about findings that are presented in the literature. So like if someone told you, here are some findings I have about the relationships between parents' education and child's education, and I have temporality, I've controlled for some stuff, and I've seen it in hundreds of thousands of people across all the countries, we would typically not be convinced that then we would believe that that's a causal effect. So I guess I'm restating some of the obvious, but I think it's, to me, a little bit striking in how different this method is versus what we typically do in good social science. this is more a statement of not should any social scientist be involved. This is more should extra social scientists be involved, and that's less clear to me. I wonder, and I think the 3 presentations outlined a lot of this already, whether extra bodies are needed. And this is related to my original point about the WLS, which is this, should we just ship it off, or is there anything that we have value added? And I think that's a real question of what is the value added by social scientists to the enterprise, conditional on having this consortium in some sense. I mean, so the consortium, I think, is really useful in examining phenotypes that most epidemiologists wouldn't have thought of, or maybe they would have thought of 30 years from now after they've plowed through all the other phenotypes in the data. And I think Dan and the group have really, shown some light on some of the, you just saw what they said about candidate studies and also gene studies. I think some of that is from the flavor of people who are trained well in statistics, so I think there's something to bring. I actually ran out of, I don't know what else we bring to it. That's really unclear to me. And related, I wonder, to the marginal social scientist thinking about this, whether GWAS uses any, almost, of our comparative advantage, and in particular, could it? Is there some kind of next step of GWAS that would say, oh, now we're going to bring in concerns and theories and methods from the social sciences into the typical GWAS analysis? This I had less to say about, but I think it is a discussion point, is what the level of interest social scientists should have in the genetic discovery component. It's related to this point of whether just having a set of findings come out of the consortium and just take, and then maybe the only step is then to take them and use them for your own interests. Whether you actually care about the SNPs that are provided in the education or in the subjective well-being, et cetera, is unclear to me. My own interest, and I know others in the room's some set of others in the room interest, is in gene-environment interactions. And so I think that's certainly an obvious step, and a step that's been taken already, and that's already been discussed a bit. I have, one set of what's next is taking the 3 SNPs, or however many we want to narrow down from the education study, and putting them on this path to then send those back to, natural scientists and say, do these make sense in any kind of animal model or mechanistic analysis? And then further, this is kind of going into a candidate gene type cycle, and then we would find some candidate genes for something like years of schooling. I have a real question about whether we just hand those off to natural scientists and say, okay, call us in 5 years and tell us what you found. If we have really anything to contribute here, that's a question. And then the other part is take them and use them in the polygenic scores that you were talking about earlier. So I think I've got an example that to talk about now about the polygenic risk score. That was surprising. So it's a little bit of a toy example. I wouldn't expect this to happen very often, hopefully, but I've been doing some work examining gene-environment interactions, asking a question, that's closer to a social science question about, do genetic factors moderate the effect of tobacco taxes on tobacco use? So, it's a health policy, economic policy, a program evaluation type question. So you have a main effect of tobacco taxes on use and ask whether that's moderated by some of the genes and SNPs we've already talked about today, some of these nicotinic receptor genes. In Haynes data, like many of these data sets are pretty quirky. This has to do with observations from the early 90s. Just to be clear what the estimate is, there's a phenotype, yes, no tobacco use. In this particular sample, this isn't genome-wide assessments of people. There's just 2 SNPs that are relevant for the analysis that were currently in the data when I analyzed them. And then the environment here is the cross-sectional variation in state level tobacco tax levels. So, well, I'll actually come back to this. I've published a little bit on this. But the point I wanted to make here, and again, just for discussion and maybe just as an example, like I said, hopefully it won't happen very often. So I constructed, based on the 2 SNPs in the data that I have, something like a polygenic risk score, the most basic you could ever do, which is 2 instead of 1 SNP, right? So within the sample, and I didn't do this right because I only had 1 sample that had everything I needed. So you could certainly be much more sophisticated than I was in constructing this. So within sample, I took the 2 SNPs and made a score, and these are the predicted probabilities for people of the the 3 types of people that could be. People have 0 protective alleles, 1 or 2, and these are their predicted likelihoods of smoking. And I took this scalar now that has values 1, 2, and 3 and interacted it with the tobacco tax, and I found nothing. Now, it turns out, and I already actually knew that something was up because I have a paper that shows there's something with one of the SNPs. And in fact, what I found is that individually what's happening is that I have 2 SNPs in the score, and I'm getting opposite and counteracting interactions, so that when you add them together and you do the interaction, you get nothing. If you separate the 2 SNPs into 2 risk scores, you get 2 interactions but of opposite effect. Now, it turns out if you go back in the literature, this is a very gross overstatement of what these SNPs and genes do, but just for quick discussion purposes, I could at least convince myself that the direction of the interactions made some sense. These would need to be replicated. But just as, like I said, as a toy example, in this particular case, I think what this is telling me anyway is that taking the polygenic scores has some risk to it. And in my case, there's actually a lot of papers on these particular SNPs and genes, so function is not as big of a black box. But for a set of a risk score that has however many 100,000 SNPs you're going to use, we know very little about each of these individual SNPs and whether we would expect the same direction of interaction with the environmental variable across all these SNPs that we're going to add together. In my case, I showed a clear false negative. But I guess the final point here is that, rightly so, most of the day we've talked about false positives as being a really big problem. In this particular case, we have the opposite issue where we'll fail to find something that might actually be there and then not know to keep looking for it, probably. We probably wouldn't keep on doing this analysis over and over trying to find something. So these are the discussion points. Should we believe the results? In part, because they really, in my view, don't overlap with how we do our own work. Whether producing new results on social sciences outcomes is an enterprise that we should have multiple consortia to doing or a single one, and then how to use the results in our own work. I've got the toy example. Hopefully that will bring up more general discussion. And that's it.
You're doing a huge public service, and I want to sort of echo what Jason's saying is then, what's in it for a little study like the WLS and then, participate. You have, on the website, you're going to have betas for score calculation that exclude every study that's participated in it. In other words, I have a disincentive to participate because once mine is in the discovery sample, then I can't use the score in my own sample. So it would be really nice to just have a system where you just check the box, exclude this, and give me the results. And or even better to have something where you don't have to start you can have a continually updated score as people from new studies want to join, and they follow the protocol, submit their results, and then they get added to the list, and the meta-analysis is just done iteratively, and allow people to kind of get something back and give something at their will.
So that is absolutely a very important point. We had a discussion about this last year, and we basically we were writing down a data sharing policy for the consortium that wanted to make sure exactly that the people who contribute towards the meta-analysis are not at a disadvantage at using the results for their own work later on. So the way that we're solving this now is that we put the meta-analysis results on the website, so anyone who has not participated can just use that information. And for those people who have participated, we guarantee that we basically redo the meta-analysis, excluding their cohort. And it's not an automatic thing, so we haven't developed a pipeline how we can automatically do that. But we're very efficient in doing that. So everyone who has requested these results from us until now, they got it within 2 or 3 days.
I think it was somebody said this morning that Genome is a homeostatic system. And even if you have a system without a feedback, and if the connections are strong, and then you impose the feedback, then all the measured relationships, they go to 0. That's a mathematical fact. So if the genome is indeed highly interconnected and homeostatic, then the measured correlations are not good indicators of the true relationships. Apart from all the non-linearity of the biochemical pathways going from the genome to the end result of the phenotype. If it is and engineers know that. They know that when you estimate, for instance, regression relationships under homeostatic condition when the feedback is on, you have to try to take care of it. I'm not saying that's easy, but you know at least one thing: the more homeostasis there is, the lower the measured relationships are going to be, even if they are in reality without the feedback loops very strong. So my thought was maybe that's one of the reasons why these effects, when in the way they are measured, are so small, if the genome is indeed a homeostatic system.
I mean, that has to be true if you think about the serotonin polymorphisms, the reuptake transporter. I mean, that effect is tiny, really. And you know that it's a big effect. I mean, that it plays we know biochemically it plays a large role in the behavior of the system in a brain slice in a dish. We know that we can totally shut it down with a drug and get a huge effect in obvious phenotypic effects. People pay a lot of money for it, so the markets tell us that they're big effects, but they look really tiny, and this has to be because of this. So, but it's hard. The thing I have to think about is what exactly you're looking for. Are you asking for a
These seem
causal
like
statement?
I don't really understand the connection. It's one thing to say you could have a biological system that plays an incredibly important role for some outcome, but variation within that system doesn't explain differences across individuals. We're not going to detect those systems using this approach. Our approach is going to detect genetic variants that have sort of measurable impacts on outcomes.
Well, so that was what I was going to say too.
Yeah, yeah. So
It depends what you want to measure.
That's right.
If you're trying to understand the mechanism, this is a bad way to do it, or it's a limited way to do it.
It's a limited way to do it. I like that.
If you're
way
trying
of
to find a
describing
marker, it finds a marker.
So I actually have a comment that relates to this point and also to one of Jason's questions about the use of the GWAS data. So the flip side of this point, that variation, that an important mechanism may not show up in variation, is that there could be important mechanisms that we learn about from small effects in terms of variation, and that there are examples of that from the medical literature. So one of the useful things that may come out of GWAS for social science at the level of identifying individual SNPs is that we may learn about mechanisms that we didn't previously know about in terms of certain traits. And another thing, actually one thing that I think is very exciting as a potential use of polygenic scores is as control variables in randomized experiments or quasi-experiments in social science. Actually, I've been lobbying Rodrigo about this for a while because I think, and to talk to Jim about it, because I think one of the a great context for this might be the Perry Preschool program, where this was a very expensive social science intervention with as a result, pretty small sample size. So this was an intervention to provide preschool to disadvantaged children and look at its effects on subsequent educational outcomes. And it's a context where statistical power for looking at the effect of that intervention is really at a premium. And if you could add a control variable that explained 20% of the variance, you could absorb some of the residual variance and improve the precision of those estimates And in that kind of setting where it's an expensive social science intervention, that could be potentially very valuable.
Maybe I can also address your comments about what social scientists can actually do with that type of work. So I think the world is going to change relatively soon because the type of data that you need to do a sensible analysis, it becomes cheaper and cheaper, and several biobanks are currently in the making, and they will have 200,000, 500,000 observations, and they will be to some extent in the public domain and be accessible to social scientists. And of course, there are many things that you can do with that data that go beyond just GWAS type of work, right? So I think in a way, data access will become cheaper and cheaper, meaning the entry barriers to what you call natural monopoly is, they're falling, which I think is a good thing.
I'm not sure. I wondered if maybe you should just grab all the data into your. It's not. That's actually not my point. It's the if I had access to Kaiser right now with however many hundred or 23andMe, if I'm not interested in discovery myself, if that's true, then that's the next question. Then what?
Right. So one thing you could do, of course, is you could take something like we've shown here in the proxy phenotype approach, where you take validated, replicated SNPs from very large scale initiatives, and you could try to figure out if and to which extent they actually relate to endophenotypes in smaller samples, endophenotypes that may not be available to others, endophenotypes that may be very interesting for you and very important for social science.
I think something you could do that would be, very much along the lines of what you were saying, where there's not enough social science yet in what's been done. And there are various ways you could bring in social science into the analysis. One thing is use methods that we're comfortable with the social science for helping to establish causality. Like, I think Dalton's going to talk about family models. You could have family fixed effects, and then, if with big enough samples with family data, you can, try to argue that that's giving you. There's a randomized experiment within the family about genotype, and so then you could more credibly establish causation. Or embed the genotypes for the SNPs within a structural model where you are modeling the different behavioral channels by which the SNP might matter. So for smoking behavior, you allow the SNP to possibly affect the marginal utility of smoking. So, or possibly affect the depreciation rate of the addiction capital stock. And then you'll learn, those different possibilities imply different patterns about the relationship between genotype and various kind of data in your data set. And so you could draw inferences then about the behavioral mechanism by bringing the methods that we know, the structural models, into this, into the analysis. So, medical people don't know how to do that.
Examples of GWAS studies that follow the example you brought up this morning, which have to do with big ones. What I mean to following is that suppose that there was make up a data set that had the differences in uniform reactivity. I would have a certain vision of the likelihood of finding something that correlates with it, as opposed to self-deployment. Put differently, the factors outside of the genes themselves that seem to be dictate something in terms of the power of the tests. And all that.
Sure.
Is that type of thinking going on?
Oh, absolutely. I mean, so there are traits. There are traits for which a few hundred observations is enough, and you can run a well-powered GWAS. Like eye color is an example, I think. It just depends on how sort of biologically proximal the outcome is.
Well, I'm asking whether or not thinking that way would facilitate the more sophisticated studies that you have some wider social science reason to have a sense of where the environmental factors are larger, relatively speaking. I'm not asking this question. Sorry.
I mean, I think that we had the expectation that the effects of SNPs on cognitive ability would be larger than the effects on educational attainment for this kind of reason. It's actually, interestingly, the evidence that we have, at least from the proxy phenotype work that Phil talked about doesn't seem to support that, that the effects we're finding are the same size as the effects on educational attainment in terms of R-squared. But we're surprised by that.
Educational attainment is much more because of this case. You're picking up two things.
Absolutely, yeah. So that's our leading explanation of it. That basically the biggest effects on educational attainment are capturing, the conditional on it being one of the biggest effects on educational attainment is probably a SNP that's working through multiple channels, not just cognitive skills, but also persistence and other kinds of, soft skills that lead to better
Possibly the
educational
same
outcomes.
is needed on both.
Yeah, exactly. So the same SNP, it's conditional on it being one of the strongest effects on education. It's probably a SNP that has that it works through many of these channels on educational attainment.
Can I ask the question that I always get asked when I talk about neuro, which is, so when does this become real economics? You guys must be asked this question all the time. How does this turn into tax policy, or how does this turn into a better model of development or growth?
Right.
You must be asked this all the time, right?
Sure.
What's the answer?
You're looking at me? Okay. Well, I mean, I think that if the genetic data are incorporated into structural models, I think that that's real economics. If we're learning about behavioral channels, especially if we're learning about behavioral channels that matter for the effectiveness of policies, I think the question of how to effectively target interventions or differential effects of policy by genotype, like the kind of work Jason's been doing, I think that most economists would consider that to be economics.
If I can add something we were discussing this morning, this is a tool. Once you have, you will have a tool where you're going to have some endowment heterogeneity prior to birth even, and it's unobserved by the parents. And you can now use this to model how revealed ability affects parental investment, for example, intra-household allocation, knowing, we observe the at least one portion of the innate ability and the parents are only having to learn it over time. I think those kind of questions that are going to be able to really integrate it into.
And I think that the timeline that you're referring to, so when does this become economics? I mean, that's a function of the sample size that we will have available for GWAS and our persistence in doing these types of studies, because, as I've shown, the polygenic score, the predictive accuracy of the polygenic score increases with the sample size that we have available. And, the higher the R-square of these polygenic scores, the greater the use in standard social science for all sorts of purposes.
But why is the question not the same that they ask people like you or me?
It was the same. It was the softball
This-
question. I agree.
why does economics need biological pathways? And when does the discovery of biological pathways become relevant for economics? I think it's the same question.
Yeah, I meant it to be the same question. I mean, and Dan basically gave the answer I always give, I think. I wasn't sure that you would, but which is structural model, structural model, structural model. And when the structural models are different or better powered or make new predictions or allow us to integrate new kinds of policies, then these new biologically driven structural models begin to, that's where the rubber meets the road. But I was curious to know what the timeline was. And I think, the answer is you guys aren't totally sure, but it sounds like you're thinking within the next 5 to 10 years.
Hopefully.
Maybe it seems to me that in the obesity literature, they have, even though they haven't found a lot, that they've been very useful as instruments. And in terms of trying to figure out the causal effects of obesity on maybe cardiovascular.
I wrote a paper critiquing the use of genes as instruments because they're highly pleiotropic. That was the discovery of the fact that we have so few protein coding genes. They must be highly pleiotropic. They're all connected. Paul, you mentioned the gene network this morning. So therefore, they're not valid as instruments. And bracketing off the argument that Felix and I were having at lunch.
Suppose that George Davy Smith were in the room. He was invoked earlier today. I've actually discussed this with him. He claims that's really third order.
Well,
How does he know?
I don't know. I don't know. I'm not a geneticist. So Gabriella's in the room. We discussed this very thing in London, what, not that long ago, right? A few months ago. And
It's probably one of these
so
things
I'm
that-
asking factually. I completely agree. My intuition says yes, we have Y-axis. But Smith was adamant.
If you had 100 variants, let's say, for obesity, or maybe 1,000, and they all showed similar effects, would your concern still be that
Sure, because
the pleiotropy could account for
yeah,
that?
because there's so many pathways. Then you're damned if you do and damned if you don't. If you have one gene, then you know, okay, for my outcome, it's working through this pathway, but God only knows what it's doing to the equilibrium in the body and affecting so many other things. And if you have 1,000 genes, then there's 1,000 different pathways. So they're all, because you have better self-control, you're not eating. That's one of the pathways, and that's going to affect whatever thing you're instrumenting for. I mean, just example of the serotonin, if I remember correct, the short allele, the quote-unquote risky one, leads to less expression of the gene, if I remember correctly, right? So you have fewer serotonin reuptake channels. That's the exact opposite intuition of what SSRIs do, because it's all equilibrium. You end up with fewer receptors post-synapse. I mean, so I think your point is that the body is forget about the social system and for these distal phenotypes, but even just the body is recalibrating and has multiple reactions to any variant.
But it's probably one of these things where we better not say not a valid predictor or instrument, but has to be really evaluated and careful, and it's probably going to be rare that it's completely correct.
It's almost in the forget about it category.
On this point of pleiotropy, we should not confuse protein coding genes, of which there are few, and the total amount of information in the genome. So there are single base pair mutations far from any genes, which actually can have huge effects. So the pleiotropy argument, I think, is not correct. I mean, there's so much information in our genome that surely there are things which have single effects.
But establishing that credibly takes a lot of work. But there might be cases
where
where
we should not anticipate that all things we discover
Right.
through GWAS will be pleiotropic. It's not. I don't think it's.
Sure.
Yeah, we shouldn't just write it off,
Yeah.
but boy,
That's
you
right.
have to be careful with it.
I agree with that.
Perhaps more basic question that they might be connected to some of these discussions about the complexity of the information. Is this a control for population stratification that is very important? You see as a big effect. I mean, it's not obviously a theoretical. I mean, there is in the back there must be a theory of why that is the appropriate way to control, and what are you really controlling for, and what is in that black box, and are we capturing some sort of systemic effects there that might be related to? So you say, oh, if I control for this, I'm killing that effect, but what are you really controlling for might be absorbing something that is important. So how do you respond? How do I interpret it?
It's a very good point.
It might be over control.
You're super cool. So I got to go to Human Genetics this year, one of the 3 trips that actually happened in October that I was able to take, like 3 days, because we were and I talked to Alpes Price and one of the people about, hey, so, and of course he was giving presentations on using PCs to correct for stratification. And if you read the original paper, which is actually pretty pellucid, it's a good read, the argument is actually pretty good for what people thought they were doing at the time, which was, we thought there would be dozens to us, a couple hundred, maybe, of these SNPs that we were hearing about. At which point, we only cared about sort of the common ones, not the stuff that was going to be specific to specific populations that would be giving you compounds. Now, I think what we're seeing, if you're spreading out the variants, the number of genes explaining the variants to thousands, tens of thousands more, now you've got a problem, because now the principal components are almost certainly picking up some of the variants of true causal variants in addition to all the other stuff.
Of course.
And it gets even worse, of course, the larger the samples you get, ironically enough. And so, I think that we're going to see maternal pedigree studies and other sorts of family designs and things like this, because there clearly has to be, and people are working on now, hopefully more powerful ways of making sure the stratification isn't the explanation, but while still retaining some of the causal explanation. So one of the reasons why I still retain hope, despite 0.2% and needing a million SNPs to do everything, is I'm guessing some of those are slightly underestimated at least, and we'll be able to recover more. Another problem, though, too, is you have to be careful about, this is another thing that came up, is that there may be groups where you really are interested in risky alleles in specific populations. Okay, so for example, Alzheimer's disease is more prevalent in African Americans. we hadn't done many ED, GWASs because not enough participants in GWASs. They have done some recently, and lo and behold, there were in fact, a few specific variants that again, if you leveled out and took out the PCs, ABCA7 wouldn't have been predicted, and yet it is in fact one of the larger, it is one larger risk variance in that population. It's almost a 2-to-1, which is huge. So it's a problem. And I don't think we have a good solution yet. But the nice thing is that, you set up the machinery, you know how to do the analyses and meta-analyses. Now somebody comes up with 2.3 or whatever it is that corrects for some of these things. No, I'm perfectly serious. You can find out, guess what? It is a little bit different, and we have the progress. But, a lot of technology, the big job is getting all these people to play nicely together. You get 140,000 samples to go on the IRBs line and all that stuff. That's actually much harder at some level than the software.
Mm-hmm.